Welcome to our lecture on electrical circuits and devices. Today, we are going to dive into a highly effective visual tool for simplifying digital logic, Karnaugh Maps. Up until now, you have likely used Boolean theorems to simplify equations. While that works perfectly fine for 2 or 3 variables, it relies heavily on your ability to spot the right rule at the right time. To remove that guesswork, Maurice Karnaugh developed a formal visual approach in 1953 while working at Bell Labs. The entire concept of a Karnaugh map, or K-map, rests on one simple proposition. If you have a sum of 2 products and they differ by only one variable being complemented, that changing variable is completely superfluous. Spotting this in a standard truth table can be tricky, but a K-map makes it visually obvious. To build a K-map, we transfer our truth table into a grid. The most critical rule here is the labeling of the rows and columns. Notice the sequence. 0, 0, 0, 1, 1, 1, 1, 0. Only one single bit changes as you move to any adjacent cell. This specific sequence is known as the gray code. Here's a quick comparison of standard binary counting versus the gray code. In standard binary, moving from 3 to 4 changes 3 different bits. In gray code, moving from 3 to 4 changes only 1 bit. This single bit change is what allows the K-map to group logical redundancies together. Let us walk through a 2-variable example. Step 1 is simply transferring the output values, f, from our truth table directly into the corresponding cells of our K-map grid. Right now, our unsimplified Boolean expression has 3 terms. Step 2 is where the magic happens. We draw loops around the ones in our grid, but there are strict rules. Loops must be a power of 2 in size. You cannot loop diagonally, and you must make the loops as large as possible. Here, we need 2 separate loops to cover all our ones. For step 3, we analyze each loop. Look at the horizontal loop. The y input stays as a 1, but the z input changes from 0 to 1. Since z changes, we drop it, leaving just y. For the vertical loop, y changes, but z stays as a 1, leaving just z. Our messy 3-term equation simplifies beautifully down to f equals y or z. Now it is your turn. Take a look at this truth table. How would you map these outputs onto a 2x2 grid, and what would the resulting simplified expression be? Here's the solution. You place the ones in the top row and the right column. Looping the top row drops the z variable, leaving not y. Looping the right column drops the y variable, leaving z. The final simplified expression is f equals not y or z. We can easily scale this up. Here is a 3-variable truth table mapped onto a 2x4 grid. Notice again that the horizontal axis uses the gray code sequence. Our unsimplified equation is quite long, so let us see how looping can clean this up. When we draw our loops, we find something interesting. One of the ones is isolated. It cannot be grouped, so its term remains unsimplified. However, look at the bottom corners. Because of the gray code, the far left and far right edges logically touch. We can wrap a loop around the map boundaries to group them together, dropping the y variable. After completing all possible loops, including the wrapped edges, we extract our final terms. We have significantly reduced the complexity of the original 5-term equation down to 4 simpler terms. Let us formalize our terminology. Any valid group of ones is called an implicant. However, the absolute largest group you can draw around a specific one is called a prime implicant. To get the most minimal simplified circuit possible, you must always use prime implicants. Never settle for a smaller loop if a larger one is possible. Moving to 4 variables, the wrapping concept becomes even more powerful. In this 4x4 grid, the entire top row and the entire bottom row are ones. We can wrap top to bottom to create a massive loop of 8. Because this loop spans across changes in w, y, and z, all 3 variables are dropped. The entire map simplifies to just not x. Here's a classic trick in 4-variable maps. If you have ones in all 4 extreme corners, you can group them all together into a single loop of 4. Because the top wraps to the bottom and the left wraps to the right, the corners are logically adjacent. This simplifies down to not x and not z. You do not always need a truth table to start. If you are given a messy Boolean expression, you can map it directly onto the grid. You simply place ones in the cells that correspond to each term in the equation. For example, the term not x means we fill the entire row where x is 0. Once the ones are placed, we fill the empty boxes with zeros. Now we ignore the original equation and just look at the grid. By drawing new, larger prime implicant loops, we can extract an even simpler version of the original Boolean expression. What if we want a product of sums format instead of sum of products? Simple. Instead of looping the ones, we loop the zeros. However, you must remember that grouping zeros gives you the inverse of the function, or not f. The result is still initially in a sum of products format. To get our final product of sums, we take that inverse equation and invert the whole thing. By applying De Morgan's theorem step by step, we break the overlines and flip the ands and ors. Double negations cancel out, leaving us with a clean product of sums expression, x and the quantity y or not z. In real-world digital design, there are often input combinations that will simply never happen. For example, a single-digit decimal display only counts from 0 to 9. The binary inputs for 10 through 15 will never occur. Therefore, we literally do not care what the circuit outputs for those states. We mark these in our table with an X. This is where don't cares become incredibly useful. On the K-map, you can choose to treat an X as a 1 if it helps you make a larger loop, or treat it as a 0 and ignore it if it doesn't. By strategically looping the X's with our 1s, we drastically reduce the complexity of the final hardware circuit. To wrap up, Karnaugh Maps are an essential visual tool for simplifying digital logic, relying on gray code and prime implicants to minimize circuits. We have covered up to 4 variables, product of sums, and don't cares. For your next steps, I highly recommend researching how to extend these rules into 3-dimensional 5 and 6 variable maps. Thank you for watching.